Look up at the night sky for a moment. Even if you can't actually see it right now, just picture it in your mind. That vast darkness scattered with points of light, stars twinkling in the distance, perhaps the moon glowing softly, the Milky Way stretching across the sky like a river of light if you're somewhere dark enough to see it. Everything you see up there, everything that exists, from that distant starlight to the bed you're lying on right now, from the largest galaxy to the smallest particle, it's all part of one remarkable story, one complete picture, one universe containing absolutely everything. Welcome to the Sleepless Astronaut channel. Tonight we're going to explore absolutely everything in the universe together. Not rushing, not cramming, just gently discovering how everything fits together, from the stars above to the atoms within. If you enjoy these peaceful cosmic journeys, consider subscribing. But right now, just relax, get comfortable. Let your body settle completely. Tonight is special. We're taking one complete journey through existence itself, understanding how everything connects, how it all works together to create the universe we live in. And we'll do this peacefully, letting each idea flow naturally into the next, like a river flowing gently toward the sea. Take a deep breath. Feel your body sinking into whatever supports you. Notice how peaceful you already feel, how ready you are to let the day dissolve and just drift through these thoughts about everything that exists. Your breathing is finding its natural rhythm now, slow and easy. There's nowhere you need to be, nothing you need to do. Just listen and drift. Everything from today can wait. Right now, we're going on a journey through absolutely everything, and you're going to feel more and more relaxed with each step we take. Let's start where you are right now, here. On Earth, your home, you're lying peacefully on a planet. A world spinning through space at over 1,000 miles per hour, though you feel perfectly still. Earth is moving through space right now, carrying you with it. But you're safe and comfortable, held gently by gravity, surrounded by air, protected by the atmosphere above. Earth is remarkable. It's a sphere of rock and metal, about 8,000 miles across, orbiting a star we call the Sun. But what makes Earth truly special is that it's alive, not just because living things exist here, but because Earth itself is dynamic, changing, active. A living world in its own way. Beneath you, far below the surface, Earth has a heart of molten metal, iron and nickel, heated to thousands of degrees, swirling and flowing in the planet's core. This flowing metal creates Earth's magnetic field, an invisible shield extending far into space, protecting everything on the surface from harmful radiation from the sun. Above the molten core is the mantle, a thick layer of hot rock that flows very slowly, like an incredibly thick liquid, moving just inches per year, but powerful enough to push continents around, to raise mountains, to shape the surface of the planet over millions of years. And then there's the thin crust where you live, the cool outer shell of rock that makes up the ground beneath your feet. Everything you've ever experienced happens on or near this thin outer layer. Every mountain, every ocean, every forest and desert and city, all resting on this delicate crust floating on the slowly moving rock below. Above the surface is the atmosphere, the ocean of air surrounding Earth, protecting everything, creating weather, distributing heat and water around the planet. The atmosphere extends upward for hundreds of miles, gradually thinning until it merges with the emptiness of space. But down here where you are, the air is thick and rich, filled with oxygen to breathe, warm enough to keep you comfortable. Picture Earth from far away for a moment, a blue and white marble floating in darkness. Blue from the oceans that cover most of the surface, white from clouds swirling in the atmosphere, brown and green from continents. It's beautiful, this little world, the only place we know of where life exists, where consciousness has emerged to wonder about its place in the cosmos. And orbiting Earth about 240,000 miles away is the Moon. You've seen it countless times, that pale disk in the sky, sometimes full and bright, sometimes a thin crescent, sometimes hidden entirely. The Moon is much smaller than Earth, but still substantial, about 1/4 Earth's diameter, large enough to affect our planet through its gravity. The Moon creates tides in Earth's oceans, pulling water toward it as it orbits, creating the rhythmic rise and fall of sea levels twice each day. The Moon stabilizes Earth's tilt, keeps our seasons regular and predictable. Without the Moon, Earth would wobble chaotically, and life might have never gained the stable foothold it needed to evolve and thrive. The Moon probably formed billions of years ago when something massive, perhaps as large as Mars, collided with early Earth. The impact threw debris into orbit, and that debris gradually came together to form the Moon. It's been orbiting Earth ever since, a constant companion, slowly drifting farther away as the eons pass. Now let's expand our view outward. Earth and Moon are part of a family, a solar system, with the Sun at its heart and planets orbiting around it. The Sun is a star. It seems special because it's ours, because it gives us light and warmth, because life on Earth depends on it completely. But the Sun is actually quite ordinary as stars go. Medium-sized, middle-aged, not particularly bright or dim or hot or cool. Just a typical star, one among hundreds of billions in the galaxy. But from Earth's perspective, the Sun is everything. It's a massive ball of hot gas, more than 100 times Earth's diameter, containing more than 99% of all the mass in the solar system. Everything else, all the planets and moons and asteroids, are just scraps orbiting this enormous central furnace. Deep inside the Sun, in its core, hydrogen fuses into helium through nuclear reactions, releasing tremendous energy. This energy works its way outward through the Sun's interior, taking thousands of years to travel from core to surface, and then radiates into space as light and heat. This is sunlight, the warmth you feel on your skin, the light that makes day possible. Energy from fusion reactions 93 million miles away. The Sun has been shining steadily for about 4.5 billion years, and it will continue for another 5 billion years before it changes, swells, transforms into something different. But that's far in the future. Right now, the Sun is stable, reliable, constant, providing exactly the right amount of energy to make Earth comfortable for life. Orbiting the Sun along with Earth are other worlds, each one unique, each one fascinating in its own way. Let's visit them slowly, peacefully, imagining what it would be like to see each one. Closest to the Sun is Mercury, a small, rocky world baked by solar radiation. Mercury has almost no atmosphere, just a trace of gas temporarily captured from the solar wind. Without an atmosphere, there's nothing to distribute heat, so Mercury experiences the most extreme temperature swings of any planet. The side facing the Sun becomes incredibly hot, hot enough to melt lead. The side facing away becomes incredibly cold, far below freezing. Mercury is harsh, barren, but it's part of the family, faithfully orbiting the Sun every few months. Next comes Venus, similar in size to Earth, but completely different in character. Venus is covered by thick clouds that never part, clouds made of sulfuric acid that completely hide the surface from view. These clouds trap heat so effectively that Venus's surface is hotter than Mercury's, despite being farther from the Sun. The atmospheric pressure at Venus's surface is crushing, equivalent to being deep underwater on Earth. Venus is beautiful from space, bright and cloud-covered, but hellish up close. Then Earth, your home, the blue world where life thrives. Beyond Earth is Mars, smaller and colder, with a thin atmosphere and a rusty red surface. Mars is a desert world, dry and dusty, with towering volcanoes and deep canyons. The largest volcano, a mountain about 16 miles high, dwarfs anything on Earth. The canyon system stretches thousands of miles across the surface, so vast it would span an entire continent on Earth. Mars was warmer once, billions of years ago. Rivers flowed across its surface. Lakes and perhaps oceans filled low-lying areas. Water carved channels and valleys that remain visible today, dried out, waiting. Where did the water go? Some froze into the polar ice caps. Some soaked into the ground. Some escaped into space as Mars's atmosphere thinned over the ages. But Mars might not be completely dead. Water still exists there as ice, and possibly as liquid water deep underground, kept warm by heat from the planet's interior. Where there's liquid water, there might be life, simple organisms adapted to harsh conditions, living in darkness beneath the frozen surface. Beyond Mars lies a gap, a region where planets don't exist, but where thousands of smaller objects orbit the Sun. This is the asteroid belt, a band of rocky debris, leftovers from the solar system's formation. These asteroids never came together to form a planet, kept scattered by Jupiter's gravitational influence, tumbling through space in their individual orbits around the Sun. And then comes Jupiter itself, the giant, the king of planets. Jupiter is enormous, more than 10 times Earth's diameter, more massive than all other planets combined. It's so large that if it were hollow, you could fit over 1,000 Earths inside. Jupiter dominates the outer solar system, its gravity affecting everything nearby, protecting the inner planets by deflecting comets and asteroids that might otherwise strike Earth. Jupiter is a gas giant made mostly of hydrogen and helium, with no solid surface to stand on. If you could somehow descend into Jupiter, you'd pass through layers of gas becoming denser and denser, gradually transitioning to liquid hydrogen under immense pressure, and possibly a core of rock and ice at the very center, though we're not certain what lies in Jupiter's heart. Jupiter's atmosphere is beautiful and violent. Bands of color wrap around the planet, created by powerful winds blowing in opposite directions at different latitudes. Storms rage constantly. The most famous is the Great Red Spot, a hurricane-like storm large enough to swallow 2 or 3 Earths, a storm that's been raging for centuries at least, possibly much longer. Jupiter has many moons, dozens of them, some tiny, some as large as planets. The 4 largest are worlds in their own right, each one remarkable. Io is the closest large moon, constantly squeezed and stretched by Jupiter's gravity, heated internally until it's the most volcanically active place in the entire solar system. Io's surface is covered with volcanoes, constantly erupting, constantly renewing the surface, making Io young despite being billions of years old. Europa is covered with smooth ice, crisscrossed with cracks and ridges. But beneath the ice, warmed by tidal heating from Jupiter's gravity, is an ocean of liquid water, perhaps 60 miles deep. This ocean is dark and cold, but it's liquid water, and where there's liquid water, there might be life. Europa's ocean is one of the most promising places to search for life beyond Earth. Ganymede is even larger than Mercury, the biggest moon in the solar system, with its own magnetic field. Ganymede also has a subsurface ocean beneath thick layers of ice. Callisto, the outermost large moon, is heavily cratered, ancient, showing a surface billions of years old with little recent geological activity. These moons, these worlds orbiting Jupiter, each have their own character, their own geology, their own mysteries waiting to be explored. Beyond Jupiter is Saturn, another gas giant, smaller than Jupiter, but still enormous compared to Earth. Saturn is famous for its rings, those beautiful structures visible even through a small telescope, bands of light circling the planet. Saturn's rings are made of countless particles of ice and rock, ranging from dust grains to house-sized boulders, each one orbiting Saturn independently, creating the appearance of solid rings. The rings are thin, just tens of meters thick in places, but they extend hundreds of thousands of miles from the planet. They're beautiful and delicate, perhaps temporary on cosmic timescales, destined to eventually disappear as particles spiral into Saturn or drift away into space. Saturn also has many moons. Titan, the largest, is bigger than Mercury and has a thick atmosphere, the only moon in the solar system with substantial air. Titan's atmosphere is so thick you can't see the surface through it, but space probes have landed there, touched the surface, sent back pictures of a strange world. Titan has lakes and rivers, but not of water. Titan is far too cold for liquid water. Instead, the lakes are filled with liquid methane and ethane, hydrocarbons that are gases on Earth but liquids in Titan's frigid environment. Rain falls from Titan's sky, not water rain but methane rain, completing a cycle of evaporation and precipitation just like Earth's water cycle, but with completely different chemistry. Beneath Titan's surface, there might be an ocean of liquid water, kept from freezing by heat from Saturn's tides. So Titan might have two separate liquid environments, methane on the surface and water underground, each potentially capable of supporting some form of life. Beyond Saturn are Uranus and Neptune, ice giants, smaller than Jupiter and Saturn but still enormous compared to Earth. These distant worlds are cold and dark, receiving very little light and heat from the distant sun. They're made primarily of water, methane, and ammonia ices, with thick atmospheres surrounding them. Uranus is unusual because it spins on its side, its poles lying nearly in its orbital plane. This strange orientation might be the result of a collision early in the solar system's history. Uranus rolls around the sun like a barrel rather than spinning like a top. Neptune, the outermost planet, is a deep blue world with the strongest winds in the solar system, storms raging at over 1,000 miles per hour. Why Neptune has such violent weather despite receiving so little energy from the sun remains a mystery. Neptune has a large moon called Triton, about the same size as Pluto, orbiting backward, probably captured from the region beyond Neptune rather than formed with the planet. Beyond Neptune is a region called the Kuiper Belt, filled with icy bodies orbiting the sun. Pluto is here, along with thousands of similar objects made of ice and rock, remnants from the solar system's formation preserved in the deep freeze of the outer solar system. And farther still, surrounding the entire solar system in a vast spherical shell, is the Oort cloud, a region of icy bodies extending perhaps halfway to the nearest star. This is where comets come from, occasionally falling inward toward the sun, developing beautiful tails of gas and dust as they're heated by sunlight. This is your solar system, your cosmic neighborhood. The sun and its family of worlds, all held together by gravity, all formed from the same cloud of gas and dust billions of years ago. It's vast, spanning billions of miles from the sun to the Oort cloud, but it's just one tiny part of something much larger. Now let's expand our view even further, out beyond the solar system, into the space between stars. The sun is one star among hundreds of billions in the Milky Way galaxy. Picture all those stars, each one a sun, each one potentially with its own planets and moons, each one shining in the darkness of space. The number is almost beyond comprehension, but it's real. The galaxy is filled with stars, scattered across a region 100,000 light-years in diameter. A light-year is the distance light travels in 1 year, about 6 trillion miles. The galaxy is 100,000 light-years across, a distance so vast that light takes 100,000 years to cross from one side to the other. The sun is located about 26,000 light-years from the galactic center, orbiting around the center along with all the other stars in our region. The galaxy is shaped like a flat disk with a bulge at the center. Most stars are in the disk, arranged in spiral arms that waned outward from the center, like water spiraling down a drain. The sun is in one of these spiral arms, and when you look at the Milky Way in the night sky, you're seeing our spiral arm from inside, looking along the disk where stars are most concentrated. At the very center of the galaxy is something mysterious and powerful. A supermassive black hole, millions of times more massive than the sun, sitting at the heart of everything, marking the point around which the entire galaxy rotates. This black hole isn't pulling everything into it. The galaxy is too large, and most stars are far enough away that they simply orbit around the center. But the black hole is there, a dense, dark heart at the core of the Milky Way. Stars come in many different types. Some are much larger and brighter than the sun, burning hot and fast, living for just a few million years before exhausting their fuel. These massive stars are blue or white, glowing with intense heat, shining with the light of tens of thousands of suns. Other stars are smaller and dimmer than the sun, red dwarfs that burn their fuel so slowly they can live for hundreds of billions of years, far longer than the current age of the universe. These stars are dim, invisible to the naked eye, even if they're relatively close, but they're the most common type of star in the galaxy. And then there are stars like the sun, yellow or white stars, medium in size and temperature, living for billions of years, long enough for planets to form and cool and potentially develop life. Stars are born in clouds of gas and dust scattered throughout the galaxy. These clouds, called nebulae, are regions where gas is concentrated enough that gravity can pull it together, compressing it until it's hot and dense enough to ignite fusion reactions. When fusion begins, a star is born, starting its long life of converting hydrogen into helium, releasing energy that will shine across space for eons. And stars don't live forever. Eventually, they exhaust their fuel and die, and how they die depends on their size. Small stars like red dwarfs will eventually cool and fade, taking so long to die that none have died yet in the history of the universe. Medium stars like the Sun will swell into red giants, engulfing their inner planets, then shed their outer layers into space, leaving behind a hot, dense core called a white dwarf. This white dwarf will slowly cool over billions of years, eventually becoming a cold, dark cinder. Massive stars die dramatically. When they exhaust their fuel, they collapse catastrophically, triggering a supernova explosion, one of the most energetic events in the universe. For a brief time, a single exploding star can outshine an entire galaxy. The explosion scatters the star's contents through space, enriching the galaxy with heavy elements created in the star's core and in the explosion itself. These heavy elements, scattered by supernova, eventually become part of new clouds, new stars, new planets. The atoms in your body, the carbon and oxygen and nitrogen and iron, all were created inside stars that died long before the sun was born. You are made of stardust, literally made of material forged in stellar furnaces billions of years ago. After a supernova, what remains of the star's core can become a neutron star, a sphere just a few miles across, but containing more mass than the sun, so dense that a teaspoon of neutron star material would weigh billions of tons. Neutron stars are the densest objects in the universe except for black holes. Or if the star was massive enough, the core collapses completely into a black hole, a region where gravity is so strong that nothing, not even light, can escape. Black holes are invisible, but we know they exist because we can see their effects on nearby matter and light. The galaxy is filled with these objects. Stars in every stage of life, nebulae where new stars are forming, white dwarfs cooling slowly, neutron stars spinning rapidly, black holes lurking invisibly. And between the stars is mostly empty space, vast distances where almost nothing exists, light years of darkness separating one star from the next. But the galaxy is not just stars. There's also dark matter, an invisible substance that makes up most of the galaxy's mass. We can't see dark matter because it doesn't emit or absorb light. It doesn't interact with ordinary matter except through gravity. But we know it's there because stars in the outer parts of the galaxy move faster than they should, based on the visible matter alone. Something invisible is providing extra gravity, holding the galaxy together, and that something is dark matter. We don't know what dark matter is made of. It's not atoms or molecules or anything we've ever directly detected. It's something else, some other kind of particle that only interacts through gravity. Understanding dark matter is one of the great mysteries of modern physics. The Milky Way is beautiful and vast, but it's not alone. Let's expand our view one final time out beyond our galaxy, into the universe itself. Galaxies are scattered throughout space as far as we can see. Billions of them, perhaps trillions, each one containing billions of stars, each one a vast island of light in the cosmic darkness. Galaxies come in different shapes. Some, like the Milky Way, are spirals, flat disks with arms winding outward from a central bulge. Others are ellipticals, smooth and featureless, shaped like footballs or spheres. Still others are irregular, with no particular shape, just collections of stars in chaotic arrangements. Galaxies aren't distributed randomly. They cluster together, forming groups and clusters held together by gravity. The Milky Way is part of a small group called the Local Group, containing about 50 galaxies, most of them small dwarfs, but two large spirals dominate. the Milky Way, and Andromeda. Andromeda is our nearest large neighbor, about 2.5 million light-years away, visible as a faint smudge in the night sky. Andromeda is slightly larger than the Milky Way, containing perhaps 1 trillion stars. In about 4 billion years, Andromeda and the Milky Way will collide and merge, their stars mixing together, creating one larger galaxy. Galaxy groups cluster into larger structures called clusters, and clusters form even larger structures called superclusters. The Milky Way is part of a supercluster called Laniakea, containing about 100,000 galaxies spread across 500 million light-years. And superclusters are arranged in the largest structures known, vast filaments and walls of galaxies stretching across the universe, surrounding enormous voids where very few galaxies exist. This is the cosmic web, the large-scale structure of the universe, matter concentrated along filaments and sheets, with emptiness in between. The cosmic web extends throughout the entire observable universe, a region about 93 billion light-years in diameter containing about 2 trillion galaxies. This is everything we can potentially see, everything whose light has had time to reach us since the universe began. But beyond our horizon, space probably continues, perhaps infinitely, filled with more galaxies and structures we can never observe. The universe might be infinite, or it might curve back on itself in ways we can't detect. We don't know for certain, but we know it's vast beyond any everyday comprehension. And pervading the entire universe, making up most of its total mass and energy, are dark matter and dark energy. Dark matter, as we mentioned, is invisible matter that only interacts through gravity. Dark energy is even more mysterious, a kind of energy that causes the expansion of space itself to accelerate. The universe is expanding. Galaxies are moving away from each other as space itself grows larger. And this expansion is speeding up over time, driven by dark energy. We don't know what dark energy is or why it exists. We only know it's there because we can measure its effects on the universe's expansion. Dark energy makes up about 68% of the universe's total mass and energy. Dark matter makes up about 27%. Ordinary matter, the stuff that makes up stars and planets and you, makes up only about 5%. Most of the universe is made of things we don't understand, invisible components known only through their gravitational and cosmological effects. The universe began about 13.8 billion years ago in an event we call the Big Bang. This wasn't an explosion in space, but the beginning of space itself, along with time, along with all matter and energy. The universe started incredibly hot and dense, and has been expanding and cooling ever since. In the earliest moments, the universe was filled with energy so concentrated that particles and antiparticles constantly created and destroyed each other. As it expanded and cooled, particles began to stick around, and eventually protons and neutrons formed, then atomic nuclei, then neutral atoms. Over hundreds of millions of years, gravity pulled matter together into the first stars and galaxies. Those first stars created heavy elements through fusion and scattered them through space when they died. Later generations of stars incorporated these heavy elements, creating planets, asteroids, eventually life on at least one planet that we know of. And here you are, lying peacefully, existing in this vast universe, made of atoms that formed in ancient stars, living on a planet orbiting a typical star in a typical galaxy among billions of others. You're part of this enormous cosmic story, connected to everything from the smallest particles to the largest structures. You've traveled far in thought tonight, from Earth to the solar system to the galaxy to the universe itself. And there's more to explore, more to discover about how everything works at the smallest scales, about the nature of matter and energy, about the fundamental forces that make existence possible. But that's for the next part of our journey. For now, rest here with what you've learned. The universe is vast and beautiful and mostly mysterious. We understand some of it, but much remains unknown. And that's okay. The mystery is part of the wonder. Feel your body completely relaxed now. You're breathing slow and natural. These thoughts about the cosmos are drifting through your mind like clouds. Beautiful to observe, but not demanding, not troubling. Just peaceful thoughts about the vast universe that is your home. Tomorrow, you can explore more. You can learn about the invisible forces and tiny particles that make everything possible. You can discover how matter and energy work at fundamental levels. But tonight is just for rest, for appreciating the beauty of existence, for drifting peacefully towards sleep. You're safe here on Earth, in your solar system, in your galaxy, in the vast universe. Everything continues around you, stars shining, planets orbiting, galaxies turning through space. And you can simply rest, comfortable and still, part of it all. So here we are, having journeyed from Earth outward through the solar system, through the galaxy, all the way to the edges of the observable universe. We've seen the largest structures in existence, the cosmic web stretching across billions of light years. And now, as you lie there peacefully, completely relaxed, let's turn our attention inward. Let's explore the other direction, the realm of the very small, discovering what everything is made of at the most fundamental level. Because everything you've seen on our journey outward, every planet and star and galaxy, all of it is made of something. And when you look closely enough, when you examine matter at its most basic level, you discover something remarkable. Everything, absolutely everything in the physical universe, is made of the same fundamental building blocks, arranged in different ways, combined in countless patterns to create the endless diversity we observe. Let's start with something you can see and touch. Your hand, for example, or the pillow beneath your head. These objects seem solid, permanent, made of continuous material. But they're not. They're made of atoms, and atoms are mostly empty space held together by forces. Imagine zooming in on your hand, magnifying it more and more, until you can see individual cells, then molecules, then atoms. At each level of magnification, new structures appear, new patterns, new organization. And at the atomic level, you discover something strange and beautiful. An atom is incredibly tiny. Millions of them could fit across the width of a single hair, and yet atoms have structure. They're not simple, solid spheres, but complex arrangements of even smaller particles. At the center of every atom is a nucleus, a dense core containing particles called protons and neutrons. The nucleus is thousands of times smaller than the atom as a whole, but it contains almost all the atom's mass. It's incredibly dense, compressed by forces that hold it together despite the extreme pressures. Protons carry a positive electrical charge. The number of protons in a nucleus determines what element the atom is. 1 proton means hydrogen, 6 protons means carbon, 8 protons means oxygen. The identity of every element is defined by how many protons it has. Neutrons are similar in size to protons, but carry no electrical charge. They add mass to the nucleus and help stabilize it, providing nuclear force without adding electrical repulsion. Surrounding the nucleus at relatively enormous distances are electrons, tiny particles carrying negative electrical charge. Electrons are even smaller than protons and neutrons, so small we can't measure their size precisely. They exist in regions around the nucleus called orbitals, areas where they're likely to be found at any given moment. Here's something remarkable to think about slowly, letting it settle in your mind. An atom is mostly empty space. If you could expand an atom to the size of a football stadium, the nucleus would be like a marble at the center, and the electrons would be tiny specks orbiting near the stadium's edges. Everything in between would be emptiness, and yet atoms feel solid. When you touch something, you're not actually making contact in the way it seems. Instead, electrons in your hand are repelling electrons in the object, and you feel this electromagnetic force as resistance, as solidity. The sensation of touching something is really just forces acting between particles that never actually touch. Think about that peacefully for a moment. Everything that feels solid is mostly empty space. Your body, the bed you're lying on, the walls around you, all mostly emptiness organized by forces. The apparent solidity of the world is created by electromagnetic forces between electrons, creating the illusion of continuous matter. Different types of atoms exist, and we call these types elements. The simplest element is hydrogen, with just one proton and one electron. Hydrogen is the most abundant element in the universe, making up most of the matter in stars and the vast clouds of gas between stars. Helium is next, with 2 protons and typically 2 neutrons. Helium is also very abundant, the second most common element, created inside stars through fusion reactions. Carbon has 6 protons. Carbon is special because it can bond with other atoms in so many different ways, creating an enormous variety of molecules. Your body is built primarily from carbon-based molecules. Carbon's versatility makes it uniquely suited for creating the complexity that life requires. Nitrogen has 7 protons, oxygen has 8, and so on up through the periodic table to heavier elements like iron with 26 protons, gold with 79, uranium with 92. All of these elements exist, each one defined by its number of protons, each one with its own properties and behaviors. And here's something beautiful. All elements heavier than hydrogen and helium were created inside stars. The universe began with only the 2 lightest elements. Everything else, every carbon atom in your body, every oxygen atom you breathe, every iron atom in your blood, was forged inside stars through nuclear fusion. When massive stars die in supernova explosions, they scatter these elements into space, spreading them through interstellar clouds where new stars and planets eventually form. Your body contains atoms from ancient stars that exploded long before the sun was born. You are literally made of stardust, made of the universe recycled and rearranged. Now, let's think about how atoms combine to create everything we see around us. Atoms bond together by sharing or transferring electrons. An atom is most stable when its outer orbitals are filled with electrons, so atoms have a tendency to form bonds that help them achieve this stable configuration. When atoms share electrons, they create molecules, structures with entirely new properties different from the individual atoms. Imagine 2 hydrogen atoms meeting 1 oxygen atom. Each hydrogen has 1 electron but wants 2 to fill its orbital. The oxygen has 8 electrons but wants 10. By sharing electrons forming bonds, all 3 atoms can achieve more stable configurations. The result is a water molecule, one of the most important molecules in the universe. Water is remarkable. A simple molecule, just 3 atoms bonded together, but with properties that make it essential for life. Water molecules are polar, meaning they have slightly positive and negative ends, and this polarity gives water special characteristics. Water molecules attract each other through these polar regions, creating hydrogen bonds between molecules. These bonds give water a high boiling point compared to similar molecules, which is why water is liquid at room temperature. Without these bonds, water would be a gas at Earth's temperatures, and liquid water wouldn't exist on the surface. Hydrogen bonds also make ice less dense than liquid water, which is why ice floats. This property is crucial for life because it allows lakes and oceans to freeze from the top down, insulating the water below and preventing it from freezing solid. Water is also an excellent solvent, able to dissolve many different substances. Your blood is mostly water carrying dissolved nutrients and gases. Cells are filled with water containing dissolved proteins and other molecules. Life as we know it depends completely on water's remarkable properties, but molecules can be far more complex than water. Some molecules contain thousands or even millions of atoms arranged in precise patterns. Proteins are like this: long chains of smaller molecules called amino acids, each chain folding into a specific 3-dimensional shape. The shape of a protein determines what it does. Some proteins are shaped like channels, sitting in cell membranes and allowing specific molecules to pass through. Others are shaped like tools that can grab onto other molecules or cut them apart. The function depends entirely on the shape, and the shape depends on the sequence of amino acids and how they fold. Your body contains thousands of different types of proteins, each one performing a specific task. Some carry oxygen in your blood. Others digest food, breaking down complex molecules into simpler ones. Others fight infections or transmit signals between cells. Proteins do nearly all the work in your body, and they're just molecules, just atoms bonded together in particular ways. DNA is perhaps the most important molecule for life. DNA carries genetic information, instructions for building and operating living things, written in a chemical code. The structure of DNA is like a twisted ladder, a double helix with 2 strands spiraling around each other. The information in DNA is stored in the sequence of molecules along the strands. There are 4 different types of these molecules, and we can think of them as 4 letters in a genetic alphabet. The order of these letters spells out instructions for making proteins, for regulating when and where proteins are made, for everything a cell needs to function. DNA can copy itself, which is essential for life. When a cell divides, it needs to pass complete copies of its DNA to both daughter cells. DNA's double helix structure makes this possible. The 2 strands are complementary, each containing the information needed to reconstruct the other. By separating the strands and using each as a template, the cell creates 2 complete copies of the original. This copying process occasionally makes errors, mutations that change the sequence. Most mutations are neutral or harmful, but sometimes a mutation is beneficial, and over many generations, beneficial mutations accumulate. This is evolution, the gradual change in living things over time as natural selection favors beneficial changes. All of this molecular complexity emerges from simple rules about how atoms bond and interact. The universe creates complexity through chemistry, through the countless ways atoms can combine and the endless variety of molecules that result. Now let's think about how molecules organize themselves into living cells. A cell is the smallest unit of life, the simplest structure that can truly be called alive. Some organisms are just single cells living independently. Others, like you, are made of trillions of cells working together. Imagine a cell as a tiny factory surrounded by a membrane that separates its interior from the outside world. This membrane isn't solid but made of special molecules that form a flexible boundary, controlling what enters and exits the cell, maintaining different conditions inside than outside. Inside the cell, thousands of different molecules float in water, interacting, reacting, working together in an organized way. At the center of most cells is the nucleus, containing the cell's DNA. When the cell needs to make a particular protein, the relevant gene is copied into a messenger molecule that travels from the nucleus to structures called ribosomes where the protein is assembled. Scattered through the cell are mitochondria, often called the powerhouses of the cell. Mitochondria break down sugar molecules and capture the released energy in a form the cell can use. They're constantly working, generating energy for all the cell's activities. The cell is highly organized, with different regions specialized for different functions. It's like a microscopic city with different districts serving different purposes, all connected by transport systems that move materials where they need to go. A single-celled organism carries out all the functions of life with just one cell. It finds food, consumes it, extracts energy, builds the molecules it needs, grows, and eventually divides to create two cells. Single-celled organisms are remarkably successful, living in virtually every environment on Earth. But cells can also work together, forming multicellular organisms. In your body, you have many different types of cells, each specialized for a particular function. Nerve cells transmit electrical signals, allowing you to sense your environment and control your movements. Muscle cells contract to create force and movement. Blood cells carry oxygen and fight infections. Skin cells form protective barriers. Each cell type has its specific structure and function, but they all share the same DNA, the same genetic instructions. What makes them different is which genes are active. In a nerve cell, genes for nerve-specific proteins are active. In a muscle cell, genes for muscle proteins are active. The same instruction manual, but different chapters being read in different cell types. Your body is a community of trillions of cells, all descended from a single fertilized egg, all cooperating to keep you alive. They communicate through chemical signals, coordinate their activities, maintain your body's functions. This cooperation is one of evolution's great achievements, allowing organisms of enormous complexity to exist. And all this complexity from atoms to molecules to cells to organisms happens because of forces. 4 fundamental forces govern how particles interact, how matter behaves, how the universe works. Gravity is the force you're most familiar with. It's what holds you to Earth, what keeps the moon orbiting Earth, what holds the solar system together and organizes galaxies. Gravity is actually the weakest of the 4 forces, but it acts over infinite distances and affects everything with mass or energy, so it dominates at large scales. Electromagnetism is responsible for light, electricity, magnetism, and chemical bonds. This is the force between charged particles, between electrons and protons. Electromagnetic forces hold atoms together, create the bonds between atoms and molecules, and generate the light we see. Most of what you experience in everyday life, from the solidity of objects to the colors you see, is due to electromagnetic forces. The strong nuclear force holds atomic nuclei together, binding protons and neutrons despite their electrical repulsion. This force is incredibly powerful at very short distances, but falls off rapidly, so it only acts within nuclei. Without the strong force, atomic nuclei couldn't exist, and atoms as we know them would be impossible. The weak nuclear force is responsible for certain types of radioactive decay and plays a role in fusion reactions in stars. It's called weak because it's much weaker than the strong force, but it's essential for stellar processes and the creation of elements. These four forces, acting on particles following quantum mechanical rules, create everything we observe. Atoms bond through electromagnetic forces. Nuclei hold together through strong forces. Stars shine because of fusion driven by weak and strong forces. Galaxies cluster through gravity. Everything emerges from these fundamental interactions. And underlying all of this is energy, the capacity to do work, to cause change. Energy takes many forms. The motion of particles is kinetic energy. The bonds between atoms store chemical energy. Light carries electromagnetic energy. Mass itself is a form of energy related through Einstein's famous equation. Energy is conserved, meaning it can't be created or destroyed, only transformed from one form to another. When you move, chemical energy in your muscles converts to kinetic energy. When you eat, chemical energy in food becomes energy your body can use. When stars shine, mass converts to energy through fusion. Energy flows through the universe, changing forms, driving all processes and changes. The universe also has a direction, an arrow of time defined by entropy. Entropy is a measure of disorder, of how spread out and randomized energy becomes. The second law of thermodynamics states that entropy always increases in closed systems. Things become more disordered over time. Heat flows from hot to cold. Concentrated energy disperses. Order gives way to chaos. This is why time has a direction, why we remember the past but not the future, why broken things don't spontaneously repair themselves. The universe started in a highly ordered state, concentrated in the Big Bang, and has been becoming more disordered ever since, spreading out, cooling, entropy increasing. Eventually, in the unimaginably distant future, the universe will reach maximum entropy. Stars will die, black holes will evaporate, and nothing will remain but isolated particles drifting through vast, empty space. But that's trillions upon trillions of years away, so far in the future that the numbers lose meaning. Now let's think about space and time themselves, the fabric of reality that everything exists within. Space and time aren't separate things. They're woven together into a unified structure called space-time. Mass and energy curve space-time, and this curvature is what we perceive as gravity. Imagine space-time as a stretchy fabric. Place a heavy object on it, and the fabric curves, creating a depression. Other objects moving across the fabric naturally curve toward the depression, and we interpret this as gravitational attraction. The more massive an object, the more it curves space-time. Earth curves space-time enough to keep you on its surface, and the moon in orbit. The sun curves space-time enough to hold the entire solar system together. Black holes curve space-time so extremely that nothing can escape once it crosses the event horizon. Time itself is affected by gravity and motion. Time passes more slowly in stronger gravitational fields, and more slowly for objects moving at high speeds. These aren't illusions. Time genuinely flows at different rates depending on circumstances. Two people can experience different amounts of time even though they're in the same universe, and both experiences are equally valid. This has been tested with precise clocks. Clocks in orbit run slightly faster than clocks on the ground because they're in weaker gravity. Clocks on fast-moving airplanes run at different rates than stationary clocks. The differences are tiny, but they're real and measurable. This means that traveling into the future is possible in principle. If you could travel at speeds close to the speed of light, time would pass more slowly for you than for people remaining stationary. You could travel for what feels like a few years and return to find that decades have passed for everyone else. You'd have traveled into their future while experiencing only a brief journey yourself. But traveling to the past seems to be impossible, at least according to our current understanding. The laws of physics don't forbid it explicitly, but every scenario for backward time travel creates paradoxes and problems that suggest nature doesn't allow it. Time flows in one direction, from past to future, and we move along with it. The universe has existed for about 13.8 billion years, and it will continue existing far into the future, perhaps forever. During this vast span of time, matter and energy flow and change and organize themselves into temporary patterns. Stars form and die. Galaxies merge and evolve. Life emerges and adapts and creates consciousness. You're part of this cosmic story, existing for a brief time in a particular place, made of atoms that have been recycled through countless forms over billions of years. The atoms in your body have been parts of stars, parts of planets, parts of countless organisms before you, and they'll continue existing long after you, becoming parts of other structures, other forms, other patterns in the endless dance of matter and energy through time. This is everything in the universe, or at least a guide to it. From the largest structures spanning billions of light years to the smallest particles that make up atoms. From the beginning of time to the present moment. From the forces that govern interactions to the energy that flows through everything. All of it connected, all of it part of one complete picture, one universe containing absolutely everything. And you're part of it, connected to all of it, made of the same matter, following the same laws, existing in the same space-time. You're not separate from the universe. You are the universe, a small part of it that has become conscious and aware, able to think about itself and wonder about its place in the cosmic scheme. This is remarkable when you think about it. Matter, just atoms and molecules following physical laws, organized itself into patterns complex enough to become alive, to become conscious, to become you. Somehow, through chemistry and biology and evolution, the universe developed the ability to know itself, to observe itself, to ask questions about its own nature. We don't fully understand how consciousness emerges from matter. It's one of the great mysteries, but it happens. You exist, you're aware, you're thinking about these cosmic questions right now, and that's extraordinary regardless of how it works. Feel yourself drifting now, your mind having traveled through absolutely everything, from the cosmic web to atoms, from galaxies to forces, from the beginning of time to this present moment. You've seen how everything fits together, how each level of organization emerges from the levels below, how the universe creates complexity through simple rules applied over vast scales. And all of this, all of existence, continues around you whether you're thinking about it or not. Stars are fusing hydrogen right now. Galaxies are rotating through space. Atoms are bonding into molecules. Cells are living and dividing. Energy is flowing from one form to another. The universe unfolds according to its eternal patterns, and you're part of that unfolding. Tomorrow, you can explore more. You can learn about specific topics in greater depth, discover new findings, understand nuances we've only touched on tonight. The universe is endlessly fascinating, with infinite depths to explore, and human knowledge grows every day as scientists make new discoveries. But tonight is just for rest. You've completed the journey through absolutely everything. You've seen the big picture, understood how it all connects, appreciated the beauty and complexity of existence. And now you can simply relax, knowing that all of this will still be here tomorrow, still mysterious in many ways, still wonderful. Your body is completely at rest now, heavy and still, supported entirely by the surface beneath you. Your breathing is so slow and shallow you barely notice it. Your thoughts are becoming softer, less distinct, merging into dreams as consciousness fades. Let yourself cross that gentle boundary between waking and sleeping. The universe surrounds you with its incomprehensible vastness, but you're safe here, comfortable, existing in your small corner of everything. You've thought about the largest and smallest scales, the longest and shortest times, the strongest and weakest forces, and now those thoughts can fade into peaceful rest. Sleep now. Dream of stars and atoms, of galaxies and molecules, of the beautiful complexity of existence, or dream of nothing at all. Either way, rest completely, knowing you're part of something vast and ancient and ongoing. The universe will be here tomorrow. The stars will still shine. Atoms will still bond. Life will still flourish on Earth, and you can wake refreshed, ready to experience another day in this remarkable cosmos. Good night, traveler through everything. You've journeyed farther than most people ever imagine. From the edge of the observable universe to the heart of atoms, understanding how it all fits together, how everything connects. And now you've earned your rest. Sleep deeply. Rest completely. Let absolutely everything in the universe fade into the background as you drift into peaceful darkness. You're safe, you're home, you're part of everything, and everything holds you gently as you sleep. The ultimate guide to absolutely everything is complete. The journey is done, and you, having explored all of reality and thought, can now simply rest, peaceful and still, at home in the vast universe. Good night, sleep well. Dream peacefully of cosmic wonders or of nothing at all. The universe, with absolutely everything in it, will wait for you. Tonight is only for sleep, only for rest, only for the gentle darkness that welcomes you now. You are made of stardust, living on a planet orbiting a star in a galaxy among billions, existing in a universe that began nearly 14 billion years ago and will continue far into the future. You're part of this cosmic story, and that's beautiful. But right now, the story can wait. Right now is only for sleep. Rest now completely and deeply, knowing you're part of everything and everything is holding you safely as you drift away. Good night. The universe will be here tomorrow. Tonight, just sleep. Rest peacefully. Dream gently. Good night.